Welcome everyone to a session on automata theory and computability. This will be the final session on designing PDA, and in this session we will also learn how to reduce the non-determinism of a PDA solution. Okay, so when I talk about reducing non-determinism, I'm not talking about converting a non-deterministic PDA to a deterministic PDA. There's a what we do is we reduce the degree of non-determinism in our solution. For this we'll take one example. Here the language L is made up of string from the alphabet set AB, and the definition of the language says A replicated m number of times is concatenated with B replicated n number of times, and the main constraint here is m should not be equal to n, or in other words, the number of A's occurring in the string should not be equal to the number of B's, and all the A's should occur before the occurrence of B. So these are the two important constraints of the given language. Okay, one is number of A should not be equal to number of B. Other one is all the A should occur before B, and the value of m and n is greater than or equal to 0. Okay, so let us design the PDF for this. So I'll keep the stack, represent the stack on the right part of the screen, which is initially empty. Okay, so for this we have to consider some examples. Okay, so we always start with the starting state of our PDA. Let me name it as 1. Okay, so this will be the name of my starting state 1, and the first question is epsilon accepted? Okay, is it accepted? See, epsilon is a string of length 0 which has 0 occurrence of B followed by 0 occurrence of A followed by 0 occurrence of B, right, where m and n value happens to be 0. But this violates the condition, that is m not equal to n. So epsilon is obviously not accepted. So I cannot mark the starting state, which is named as 1, as accepting, right? So this is not accepted. Okay, now let me take another example. So we will take an example which has, first let us take an example which has more number of A's. Okay, so I'll keep 2. Okay, let me take 4A and 2B's. Okay, so this is obviously valid according to the definition of the language. So what we'll do, for each A we'll push A onto the stack, and I'll remain in state 1. Okay, so for the first A I'll push A onto the stack. So this will be the content of the stack after encountering first A, and since I'll remain in state 1, for the rest of the remaining 3 A's I'll perform the push operation. Okay, so this will be the content of my stack after I encounter 4 A's, right, and I'll remain in state 1. Okay, now when I encounter B, I have to make a transition to another state. So this transition is made only to make sure that after A I should get only B, right? Once I start getting B, I should not encounter further B's. So I'll make a transition to state B. Okay, what are we supposed to do? We need to perform pop operation for every B. So B, if top of the stack is A, then I'll perform pop operation. So what will be the content of the stack for the first occurrence of B? I'll have only 3 A's in my stack, right? Okay, then being in 2 state, if I encounter further B's, I'll perform the pop operation. I'm popping A out, right? Okay, for the second B, I'll perform one more pop operation. Yes. So this will be the content of the stack after I encounter the entire string, that is 4 A's followed by 2 B's. Obviously this should be accepted, isn't it? Now because and 2 state 2 should not be marked as accepting state. If I mark state 2 as accepting, then it will accept equal number of A and B. For example, if I take A, which has m equal to n, this will be accepted if I mark 2 as accepting, but this should not be accepted, so I will not mark 2 as accepting state. Okay, now what do I have? I don't have any further string to encounter, but I have I have some A's in my stack, right? And the condition for PDA very clearly says the state should be in accepting state, the finite state should be in some accepting state, and the content of the stack should be empty, right? So these two contents somehow need to be removed and I have to end up in some accepting state. So what I will do is I'll make a transition, epsilon transition, then I'll pop out the remaining A's, right? So this A is popped out, and I'll make a transition to a state called as 3. Let me name it as 3. Okay, so what happens directly after popping 2 A's out, when I don't encounter anything, because we have come to the end of the input string, right? I'll go to state 3 by making an epsilon transition and popping A out, right? Now I am in 3. Still I have more A's, sorry, I have popped A. Still I have more A's in my stack. So what do? I'll remain in 3 state and I'll perform pop operation. Okay. Yes. So this A is also popped out. Okay. Now what did happen? For every A, we have pushed A onto the stack and we remained in state 1, and when we encountered B, we made a transition to a state 2 by popping A out. And if I have more number of A's, then I'll make a transition to a state 3. Okay, I'll make an epsilon transition to state 3 and I'll pop out the remaining A's out, right? So I'll go to state 3 only if I encounter more number of A's, right? Okay, so this is how the solution works if I have more number of A's. But we are not done with the solution. Another scenario is left out, that is if I encounter more number of B's, right? Let us take that example. Okay, I'll take some 2A and followed by 4B's. Okay, yeah, for the first starting state is 1. For the first A, I'll push A onto the stack. I'll remain in state 1. Then for the second A, I'll also perform the push operation and remain in state 1. Then for the B encountered, I'll go to state 2 by popping A out. And for the next B, for the second B, again I'll perform a pop operation by popping A from the stack. Okay, now we have ended up in, so after encountering AA and BB, after encountering till here, I am in state 2 and my stack is empty, right? Okay, now what do we have further? We have further more number of B's, right? So I should make a transition to some one part of the solution scenario is clear, that is the stack is empty, but I am not in an accepting state. So what we need to do is, for further occurrence of B, I have to make a transition to a new state that will eat up all the remaining B's, right, or ignore the remaining B's. Okay, so for the this B, I'll go to state 4 by not performing any push nor performing any pop operation. So this B the third B, sorry, the third B is ignored, right? It is consumed, and the transition is made to state 4, right? And for the final B, I'll remain in state 4, and I'll simply consume it by not performing any push nor pop operation. Okay. Now, at the end of the string, after encountering 2 A's followed by 4 B's, I ended up in state 4, and my stack is empty, right? And 4 is an accepting state. Okay. So we have state 3. We go to state 3 only when we encounter more number of A's in my string, and I'll go to state 4 when I encounter more number of B's in my string. So this is the solution for the given language, where M is not equal to N, or number of A is not equal to number of B's. Okay, but this problem is highly non-determinism, right? It has high degree of non-determinism, because if you observe from state 2, you can make a transition to 3 by not reading anything. That is, you can make epsilon transition, and you can, for B, you can remain in 2, and in one scenario you're going to state 4, right? So this will add a lot of non-determinism to our solution. So what we can do is we can reduce the non-determinism by following some steps. Okay, by having some new tools that will help us in reducing the non-determinism. We'll see how to reduce the non-determinism soon. So, but before that, I hope this particular solution is clear. The degree of non-determinism in our solution can be reduced by using two powerful tools, two symbols, hash and dollar. Okay, hash is the bottom of the stack marker, and dollar is the end of the string marker. So using these two symbols, we will be very sure if the string contains more number of A's or more number of B's. Okay, so what do we do is, initially we will push hash onto the stack before encountering any A's. Then we'll append dollar at the end of our string to make sure that the entire string has been read. Okay, so these two symbols will act as a guiding point in determining whether I have more number of A's or more number of B's. So to get a clear idea, we'll take some example. Okay, first let us consider a scenario where I have more number of A's. So as previously said, what I will do is, before encountering, so if I take some example, okay, so we'll take some example. I have more number of A's. Okay, and I have here, in this case, I have 4 A's and 2 B's. So what we will do is, we'll make use of these two symbols, bottom stack marker and dollar, in our operations, to determine whether the string is accepted or not. Okay. So initially, before reading any string, I will push, or the PDA will push hash onto the stack. Okay, so this hash will be pushed onto the stack. So to incorporate this operation, we need to have a new starting state, right? So let me name it as 0. So 0 will be the new starting state, and what do? We simply perform push operation. Pushing hash onto the stack. Okay, so upon epsilon, hash is pushed onto the stack. Okay, so we have hash. Initially we have hash. So in this case, we have before reading this A, I have pushed hash onto the stack, right? Okay, and at the end of each string we will add dollar. Okay, so this will guide us or guide the PDA to make sure that the end of the string is encountered. Okay, so we will encounter dollar only after reading all the A's and B's in our string. So using these two symbols, let us solve this particular problem. Okay, so we always start with state 0, and what did we do? We pushed hash onto the stack. Now we start encountering A's, right? So when I encounter the first A, I'll push A onto the stack. I'll remain in one state, right? For the second A also I'll push A and I'll remain in state 1. Okay, so after reading 4 A's, I'll remain in, I have ended up in state 1 by pushing, right? Pushing A. Now when I encounter B, I'll go to state 2 by popping A out, right? Okay, so for the first B, we will pop this A out, and for the second B, I'll pop another A out, right? So this will be the content of the stack after reading 4 A's followed by 2 B's, right? Okay. Now, what do we encounter? Now we encounter dollar, right? So when I get dollar, I'm very sure that all the A's and B's have been read already, right? So I will not encounter any further A's or B's, right? So when I encounter dollar, what does that indicate? That indicates I have more number of A's in my string, right? Okay. So instead of having an epsilon transition here, what we can do is we can write dollar here, right? Okay, so while reading dollar, I'll go to state 3, and in state 3, what do I do? So obviously for the dollar encountered, I'll pop this A out, and in state 3, when I encounter further A's, I'll perform pop operation. Okay, and what do we have on the stack? When I pop all the A's out, I'll be left out with the hash symbol, right? So even that need to be popped out. Okay. Okay, so epsilon popping hash, right? So what do we have at the end? We ended up in state 3, which is an accepting state, and my stack is empty. So this has reduced the non-determinism to a certain level because there is no epsilon transition from state 2 to state 3, right? We have a transition to state 3 only when we encounter dollar, right? So this will reduce a non-determinism in our solution. Okay, so this is for a scenario where we have more number of A's compared to number of B's, right? And we did not get a clear idea when or how the bottom of the stack marker has helped in reducing the non-determinism, but we have understood how this dollar symbol has reduced the usage of this dollar symbol in our string at the end has reduced the non-determinism in our solution, right? Now we'll consider one more scenario. So in this scenario, I have less number of A's and more number of B's. So obviously we have to append this at the end. So in this case, what will happen? We'll start with the starting state, which is 0. So initially what do? We push hash onto the stack, right? And make a transition to state 1. Okay. Now in state 1, when I encounter A, I push A onto the stack, and for the second A, again I'll perform the push operation. Now when I start encountering B, I'll go to state 2 and perform a pop operation. Okay, so this 2 A's will be popped out. Yes. Okay, so till here we are done, right? 2 A's and 2 B. So this will be the content of the stack. Now for the further B, what do I do? For the further B, if the top of the stack happens to be epsilon, if the top of the stack happens to be hash, then I'll go to state 4, right? B, top of the stack, if the top of the stack is hash, then I'll perform the pop operation. Popping what? Popping hash. Okay. Now I go to state 4. In state 4, for the further B's, what do? We simply consume the remaining B's. So this will remain as it is, right? So this transition will remain as it is. And after reading all the B's, what do I encounter? I encounter dollar, and for that dollar also we simply consume, right? Yes. Now this again has further reduced the non-determinism in our solution, right? So when do I go to state 4? I go to state 4 only if top of the stack is hash, right? So this will be the scenario when I have more number of more number of B's in my string. Okay, so using these two symbols, we reduce the non-determinism in our solution, and this can be applied for all the previously solved problems. Okay, so this is about PDA and also reducing non-determinism in our solution. Okay, I'll see you all in the next one. Thank you.